Hey CIS, today's the same day, but we're going to do another lesson. So that's why I didn't change clothes in case you're watching this on another day. But we're going to talk about independent events. Dependent is when something forces another option to happen. Independent is when they're completely separated. So if I draw a card from a deck of cards and put it back, we have no influence on the next card that I'm drawing if I shuffle each time. So those would be independent events. We can do independence. If they're truly independent, the intersection is simply the multiplication of my two probabilities. We have been doing this since the first lesson, so we just haven't talked about the fact that they're independent or not. Two cards drawn from a deck of 52 cards, replacing what is the probability that both cards are aces. So there are 4 aces in 52 cards. Again, we're going to put it back. So there's still 4 aces and 52 cards. So to find the intersection of that happening, or the both happening, the and, we've got 1/13 times 1/13, a probability of 1/69. We've been doing this for a long time. Okay, a word problem. A grocery store warehouse encourages customers to buy in bulk. Hey, look at us right now. This is happening. On any given day, 80% of the customer sales amount to more than $125. In other words, any given sale has a probability of 80% of being more than $125. Assume that the first several sales of the day can be treated as independent, meaning customer 1 does not influence customers 2 amount of sales. What is the probability that the first two sales on Monday are both more than $125? In other words, the probability the first sale is bigger and the probability the second sale is bigger. Equals, since they're independent, which it says right here, we can take each probability separately and multiply. So 80% times 80% is a 64% chance that both will be greater than $125. What is the probability that exactly one of the first 3 sales is more than $25? Now this is where it gets a little bit complicated, because it could be the first, could be the second, or it could be the third. So whenever we get or, that's when our brain starts to yell and. Or is add, and is multiply, and that's what we've been, and is here, multiply. So let's dig into this one. Again, we could do the first way, the second, or the third customer. So there are 3 ways that the first 3 sales can be more than 125, and we get that from the fact that order does not matter, combination. So the probability of having 2 parts, first decide how many ways that we can have one sale out of greater than 125, and the probability of one greater than 125 and not 2 greater. So because there's 1 yes and 2 no's, we've got to include both. So the probability part is 80% for 1 sale, 20% for 2 sales. So the probability part is 0.032. However, order does not matter, so we have to multiply that by 3, saying that it could have been the first customer like we did here, or it could be 02, 08, 02, the second customer, or it could be the third customer, 02, 02, 08, but all of those are going to multiply the same number. So we can just say there's 3 ways times 0.032. We have a 9.6 chance of one of the first 3 sales being greater than 125. So we always have to look at, does the order matter in these problems? If a coin and a dice are tossed, so we got a dice and a coin, opposite, what is the probability of getting a tail and a 4? The dice doesn't influence the coin doesn't influence the dice. With both of that saying, we can say it's a 1/2 chance and a 1/6 chance. Since they're independent, we can multiply those together. We get 1/12. 5 dice are rolled. Each dice would be independent. What is the probability of getting exactly 3 4s? Let's tackle this question first. Okay, we have to look at 3 of them as favorable and 2 of them as not favorable, not 4s. Again, we have to say that order doesn't matter, so we've got 5 choose 3, making them 10 different options of getting 3 there. So the probability section is 1, 2, 3, 1/6. Those are my 3 4s. And 1, 2 sets of 5 6. Those are the 2 that are not 4s. There's the probability section. But remember, there are 10 ways because order doesn't matter. So we multiply that by 10, we get 250 out of 776, reduce that down to 125 over 3,888. We have to include the favorable and non-favorable, as well as the number of options if order does not matter. 3 pieces to these. So for part 2, we're talking about getting at least 3 4s. So you could have 3 4s, 4 4s, or 5 4s. That's what you said. Do this the same way. So we already had the probability of this. Okay? Probability of 4 4s would be 1/6, 1/6, 1/6, 1/6. Those are the 4 favorable options times 5/6 times 5 choose 4. Then we need to do probability of 5 4s, which would be 1/6, 1/6, 1/6, 1/6, 1/6. That one is this one. We did that one. We did that one. We did that one. Since they're all 5s, we don't have a combination for this last piece. Since it's an OR situation, we add each of those probabilities together, giving us 276 out of 7776. Reduce down, you can always math frac that in your TI calculator. All right, these are intense, I know it. There is a formula for it. These are called binomial probabilities. Okay, so there's the 3 pieces in binomial probabilities. This piece shows that order does not matter. That's the combination piece. The next section is the probability of the favorable thing. This is what we want to the number that we want it at. So in our last problem, we had 1/6 4 times because we had 4 4s coming out. The last piece is the number of unfavorable outcomes. So we had 5/6 here, and to the number of how many unfavorable is. So if we had 5 dice, we were getting 4 of them to be 4s. We had 1/6 to the 4th, and 5/6, those are always going to be complements of each other, to the 1, because 4 plus 1 gives us our total of 5 rolls. And we had 5 choose 4 multiplied by that. So we were just doing the binomial probability. This last problem that you saw is a binomial probability problem. There's your favorable outcomes. There is your unfavorable outcomes. There's 3 of those. There's 2 of those. And we said 5 choose 3 was that times 10. So this is a binomial probability problem. All right. So last example. Baseball player has a well-established career, a batting average of 300. Hey, that's pretty good for a baseball average. In a brief series with a rival team, Scott will bat 10 times. Find the probability that he will get more than 2 hits in the series. All right, loaded question. We want to get rid of that. It's easier to do the complement here. So if we got more than 2 hits, he could have 3, 4, 5, 6, 7, 8, 9, 10. Let's, instead of doing all 8 and adding together, let's find the probability of 0, 1, or 2, and then getting rid of that total. So for the complement, we have probability of success is 0.3, which makes a probability of failure 0.7. To get 0 hits, we have 10 choose 0. These should be exponents. 0.3 to the 0, 0.7 to the 10, because he would fail 10 times. The probability of getting 0 hits is 0.02, or just under 3%. The probability of getting 1 hit, 10 choose 1, 0.3 to the power of 1, 0.7 to the power of 9. We put all those together, we have 0.1211, or about 12% of getting 1 hit. Probability of getting 2 hits, 10 choose 2, because it doesn't matter what order he gets his hits in. Probability of success is 0.3 to the 2. Probability of failure is 0.7 to the power of 8. Getting that multiplied together, probability of 2 hits being about 23%. So the probability of getting 0, 1, or 2 hits, we add those together and we get our we add those 3 together right here, and we got our 0.3828. Again, that was not what we wanted. We wanted the probability he would get more than 2 hits, so we're going to take the complement of that, 1 minus. So he has a 61.72% chance of getting more than 2 hits. Again, we had our binomial probability 1, 2, 3 times. They're all separate because you can't have 0 hits and 1 hit simultaneously. So that's why we were able to add those 3 together, giving us our grand total of 61% chance. Alrighty. This one's the last one, sorry. Certain state, it has been shown that 50% of the high school graduates who are capable of college work actually enroll in colleges. Find the probability that among 9 capable high school graduates in the state, exactly 4 will enroll. 4 through 6 will enroll. So these are binomial probabilities. Here's your answers. Hopefully you can figure that out. This is one I would have you do in class as kind of an exit ticket. See if you can get those. Make comments if you need help. Please post any that are too confusing. I will be checking it frequently until March 30th, but daily as of March 30th. We'll get you help if you need it. Have a great day, you guys.